My name is Nick Harbour. I'm an incident responder with Mandiant. I specialize in malware analysis. I do most of the malware analysis and as well as malware analysis training for our company. Let's go ahead and get started. This presentation is going to cover both online anti-forensic techniques as well as like dead disk anti-forensic techniques. Both you kind of need a two-pronged technique for providing stealth malware. A lot of the techniques we are going to be covering here are things that I've observed, and as well as other people in our company observed throughout our incident response experience. But other ones are going to be things that I've actually developed through my own research, as well as existing research in the field. Everything in this talk is going to be things that are not rootkits. Basically, what malware can do that's not a rootkit to provide some level of stealth. Honestly, we don't actually encounter that many rootkits in our incident response work. There's several theories about that. One may be that rootkits cause a lot of blue screens, things like that. For whatever reason, these techniques are actually the most predominant things that we're finding. This talk, I've kind of designed it aimed towards the bad guy. I want to teach you techniques that can help you write your malware to make my job a little more interesting. These techniques can be used by the good guys as well, so you know that what maybe the actual bad guys are doing. But honestly, most of the malware you actually get is pretty lame, so if you can make my job a little bit better, that's pretty good. So like I said, there's something here for everyone. This isn't one of those talks that's going to come in right at the very top level, showing all this very obscure aspects of the Intel architecture or something like that. I'm going to kind of cover a broad range of topics. Some of them might be a little over your head. Some of them might, if you have been doing a lot of reverse engineering, you might think they're kind of rudimentary. But they're actually valid techniques still, and they're still being used to provide stealth. Most of the techniques are going to be used on Windows because, honestly, that's where most of our malware we're finding is on. But I am going to cover Linux techniques. Specifically, the new research I'm uncovering is going to be specific to Unix environments. It's actually fairly portable. I've only really tested it on Linux, though. I also mentioned that there will be something in the end for the good guys. There's a new tool we're releasing, and we have a whole box of them. I think wherever he went, Mike Graven over there, you can stop by there. We have CDs given away, other prizes. That CD. We'll cover that at the very end of the talk, though. So this talk is going to be mostly about evil. And maybe if we have time, I can show you something good. Anybody have a problem with that? So, all right. I figure this is the BlackHat crowd, so might as well be pretty evil. So we're going to start out with live system anti-forensics. So this is things when we first respond to an incident. We go to a host machine. We do what we call like a live response. We look at the running system and see what's going on. So I'm going to cover some techniques that are going to kind of masquerade running processes and do things like that to thwart a live forensic process, as opposed to like the talk yesterday where they found some bugs in the file systems or something like that you can exploit to prevent people from looking at something in in-case. I'm going to call those offline anti-forensics. Purely my terminology. I don't know if there's an industry standard out there, but I'm not going to waste my time researching that. I think we all know what I'm talking about. Once again, no rootkits. Okay, so the first thing I'm going to talk about, I know there's been a lot of talk about this, so I'm not going to spend a lot of time on it, but basically process injection. This is becoming a little bit more common in malware. Because still, even though it's been around for a little while, not everybody is totally up to speed on it. The first method is what we call hook injection. This basically, you can utilize the Windows hooking mechanism to intercept events and get malicious code to run in pretty much any arbitrary process you want, as long as you have the proper privileges. And whenever we get code to run in another arbitrary process we want, we're running as that process. So we have all the rights and everything of that process. So if, for example, the user has allowed the Windows Update service to bypass the host-based firewall, and I insert code into that, then my process, my malicious code, then has bypassed the host-based firewall. So very easy to do and very effective. And also, now I don't see a process named malicious.exe or something running. I have, the Windows Update service, or I have Internet Explorer running, and I have my malicious code running as part of that process. So hook injection basically uses, this is actually the easiest method. There's 3 main methods. I'm going to go through the easiest. Some of my colleagues yesterday in a talk revealed a new method using the kernel, but I'm sure new methods are going to be added all the time for this because it's fairly sophisticated and you can do a lot of, it's very powerful. So the first one uses the set Windows hook X function. It's it's the second layer down in the Windows API. You can do a little bit more with it than the higher level ones. But basically, when we're adding hook code to a process, so I want to hook like mouse events, using this function, I can actually specify a DLL of my choosing to intercept that call, so which I can have arbitrary code. There's kind of a very oversimplified view of the Windows message hooks. It's a lot more complicated, but this is the Fisher-Price model. Whenever you're writing a malicious DLL and you want to hook this method, you're going to have to be sure at the end of your DLL to call this call next hook X function. Otherwise, that hook is not going to be passed on to the underlying application. So let's say I'm trapping keystroke events and I'm hooking into Internet Explorer. Well, once I make that hook, if I'm not calling this function, Internet Explorer is not going to get those keystrokes. And then Granny is going to take her computer to Best Buy and say, I can't surf the Internet. And of course, the Geek Squad's just going to automatically reinstall Windows. That's all they know how to do anymore. So, I apologize to any Geek Squad employees, but you know it's the truth. There you go. Okay. So here's the basic code for hook injection. I apologize for C code so quickly in the slides, but just look at the highlighted functions. These are the main Windows API functions, and we're going to cover them a little bit more in detail. But mainly note load library, then get proc address, and then set Windows hook X. Actually, I will spend a little more time on them. So load library, I need to specify the DLL here. I've named the DLL evil.dll. Of course, in real life, it's not going to be named evil.dll. It'll be, something a little bit more cleverly named to hide itself. In this case right here with set Windows X, I've hooked WH call Windows proc. There's lots of different hooks you can actually hook onto. And actually, I can have several different malicious DLLs hooking different things or all hooking the same thing. This one's a little bit more destructive than others. There's one called like CBT. There's a CBT hook for computer-based training. Nobody ever actually uses it. So you can pretty much hook that one and be guaranteed to not really screw anything over. The next one is called library injection. This is probably the most common we actually see in the field. Just because it's a little more straightforward, we don't have to worry about a lot of things. Like with the message hooks, we don't have to worry about it crashing the OS. And with the later technique, we don't have to worry about all this tricky things we have to do with our actual malicious code to get it to actually work. So this one, basically, we're going to load a library in, and every time that library gets loaded, it's going to call this DLL main function. So we put our malicious code into DLL main as the exported function of the DLL. DLL is just a library of code, a library of functions. So the malicious one that's going to be called is this DLL main. So what we do is we basically just Windows is so nice that they've created us a whole suite of functions in their API for manipulating other processes. Why they chose to do that, I'm not really sure. I come from a Unix background, but that sort of thing just doesn't quite set well with us. Windows, I guess, came from a different philosophy. So the one we use maliciously here is create remote thread. Basically, I can create a new thread of execution in another process. Like I said, it's kind of questionable the legitimate uses of that entirely, but I think anytime you legitimately want to use that, it can probably be done better another way, but it's in there. So we use create remote thread in addition with this load library function. So whenever I create a remote thread, the basis of a thread has to start executing somewhere. So what I want to do is I want to start it executing on this load library function, and load library then is going to load our malicious DLL. And when you use the load library function, the first thing it does, well, it loads it into memory, then it calls that DLL main to do any type of initialization that needs to be done. Which in our case is going to be something malicious. I might spawn a reverse shell or something like that, whatever I want to do. That's up to you guys. I'm just showing you how to get it done. So there's an extensible allocation function called virtual alloc_x. Basically, what I need to do to get this function to work, I'm going to need to allocate just a little bit of memory in that other process. Not a huge chunk, just a little bit. And then I'm going to need to fill that with something. And here's what I need to fill it with. Basically, apologize again for the C code. This is fairly simple C code, though it kind of maps back to pretty much any programming language you want to use. Okay, so we have virtual alloc_x. You can see this hproc, don't worry about it, it's beyond the code of this thing. I just want to get as minimal code in here as possible. But basically, I've opened up another process. I'm going to allocate something in there. I'm only going to allocate this much memory where it says evil DLL up at the top, lib path. I just want to allocate enough data for that string in that other process. And then I'm going to write process memory. So I'm going to copy that string, the evil.dll. I'm going to copy that string over to that other process, purely through using the Windows API. Very simple to do. They intended this behavior. We can use it for evil. And then we're going to create remote thread. So now I have this string in that other process. I can just call create remote thread with load library and point. And so the argument of load library is going to be that string, and it has to be in that other process. Otherwise, I can't use it as an argument to that new thread. Don't worry too much if you don't understand the full details of how that actually works. But if you're doing any malware analysis or reverse engineering and you see these sequences of functions happening in this order, you pretty much know right off the bat you probably have this type of library injection. And tools like IDA Pro make that fairly easy to see exactly the sequence of functions that are being called. The next method is called, well, I just call it direct injection. I'm kind of giving these my own names because as far as I know they haven't actually been officially named. So I just call this one direct injection. Basically in the last one, I told the program to load a DLL, that all my malicious content is going to be in that DLL. This one, I'm not going to load a DLL, I'm just going to stuff a big chunk of executable code into it and have it execute that in a new thread. So it's a little bit more complicated because a DLL provides all the nicety things you might want. Like it's all relocatable, so a DLL can be anywhere in memory. It's automatically, there's loaders for it, it knows how to load it. Whenever I'm directly injecting code, it's not quite so nice because I could be kind of anywhere, the execution can be going anywhere, and there's not this automated mechanism to get that to happen. So it's more cumbersome in code, and honestly, it's probably going to be a little bit more buggy. Oop. I didn't actually put the code in here because it's in the last few examples I could kind of condense it all down to one page, but it was kind of a bit more code that I can reasonably fit on one slide. And I've been to some other talks here this class where they fit an unreasonable amount of code on one slide, so I figured I'd spare you. Okay. Next few things is registry evil. Some of you guys might say, "Oh, this is really lame," but it's really lame. But still, if most people don't know it, it's still very valid. So just using the Windows registry, I can make evil things happen. The first one I'm going to talk about here is image file execution options. Basically, there's a registry key that lists, has a list of executables, and every time that executable is run, these certain execution options are applied to that executable. And one of them that's particularly evil is this one called debugger. So with debugger, I can tell it I want this other executable to run instead of this one. So here in this example, I'm using calc. Whenever the calc command is run, calc.exe, I'm actually going to be running Notepad. And Notepad is going to be passed the argument of calc.exe. And if I ran calc.exe with a few command line options, those will also be passed on that command line. So then it's up to this notepad.exe process to invoke my new command as a debugger and establish that relationship. So there are legitimate uses for this, but it can also be used in our case for evil. So if I made a malicious program, I can attach it and have it run this way covertly by just telling it it's really a debugger for, like, I don't know, calc or some other program that's commonly used. I don't know, maybe Firefox. So if I attach my program as a debugger for Firefox, then every time Firefox is launched, my program is actually going to be launched. Of course, now my program needs to know how to launch Firefox, which is fairly easy. You just run Firefox. So, next evil thing is called app init DLLs. Basically, there's another registry